Welcome. Today we look at the method of integration by parts. It's all based on the product rule. Let me write down that rule. If you take the derivative of a product of two functions, then we get the v u prime plus u v prime. Now if we integrate this rule, we get uv is the integral v, and I just write du. du over dx times dx is du plus the integral u dv. Now we can solve for one of these integrals, and we get the integral u dv is equal to uv minus the integral v du. So that's the formula which we have to remember, which allows us to integrate by parts. Let's just look at an example. So if we have the integral x times cosine x, so what we can do is we can we think about x as u, and cosine x dx, we think about this as dv. Now if we integrate dv, we get the v, so we get uv. So what we do is we integrate that, and we get x times, and when we integrate cosine x, we get sinus x, and then we subtract the integral where we take the derivative of u, which is 1, and we take that v which we already had. So it is the sinus x dx, and we end up with x times sinus x plus cosine x plus c. So we have found our antiderivative of x times cosine x using this rule here, which is based on the product rule. So in all the examples which I'm going to do, we will start with a basic example, then doing more advanced examples, and then even have a very cool method called Tic-Tac-Toe. I want to kind of tell you how we can streamline this a little bit. So I will always kind of just actually skip u and v and just identify what we integrate and what we differentiate. So what we have done here is we have differentiated x. Right? This comes in here as 1, and we integrated cosine x. So what we do is we have an expression which is a product of two functions. We integrate first, have no integral anymore, we integrate this, we get sinus x here, x times sinus x, and then we write down minus another integral where we both differentiate and integrate. Okay, let's look at the following example. We want to integrate x times e to the 3x. Now, this is a product of two functions. We identify the function which we want to integrate and the function which we want to differentiate. It's usually good to differentiate polynomials. We will come back to this. So we differentiate this and we integrate this. So what we get when we do that is, first of all, we write down the expression where we just integrate. So e to the 3x over 3, that's the derivative. The derivative we have not yet taken here, but we have just integrated this. And then we integrate where we both differentiate and integrate. So it's 1 times e to the 3x third. And we know how to integrate this. So this is x times e to the 3x third, and then minus e to the 3x over 9 plus constant. This is our final result. Before we come to section 3, I want to squeeze in another example, the integral of log of x. How do we integrate this? We don't have a product of two functions, but what we can do is we can just add another function, 1, And so now we don't want to differentiate that. That would be silly. We can also not integrate that very well here, so we actually differentiate this and integrate that. So let's just see what we get. The first expression we write down just integrates, and we do nothing with this, so it's log x times x. And then we subtract an integral where we do both, where we integrate and differentiate. So when we integrate here, we get x, and if we differentiate this, we get x in the denominator. And this is nice, this is 1. This is log of x minus x times x minus x plus. So this expression you might remember from the entropy. But this would be hard to guess if you would not know this method of integration by parts. Okay, in this example we also have here a polynomial, a trig function. Polynomials we differentiate. We want to differentiate, so I can put that here, differentiate this, then we will integrate that. The reason why we want to differentiate this is because it becomes simpler if we differentiate it. So this is, in the first expression we write down, we just integrate and we don't do anything with this. So sinus x. Now we subtract the integral where we both differentiate and integrate. You see we end up again with an integral which can be done by integration by parts. So again we have to differentiate. We differentiate this and integrate that. Let me just write that down. X squared sine x doesn't change. Here we write down the expression where we just integrate and don't do anything here, minus 2x. And if we integrate sinus x, we get plus a minus cosine x, so this becomes a plus sign. And then we write down the we write down, so we have a minus cosine x here, so we have minus minus, which is plus the integral, and then we have 2 here, differentiate this, and we integrate that, so we have integrated that, that was a minus cosine x. So so what we have is with a minus sign here, because it was minus. And this we know how to integrate, so that's x squared sine x plus 2x cosine x minus 2 sinus x plus c. You see we struggled a little bit here with the minus sign. So there was a minus sign from here, then there was a minus sign because we do again integration by parts. So this minus sign, then the minus sign from the cosine x. So that can be a little bit tricky, and that's why there's a much better method to do that, keep track of these minus signs. Okay, in this next example we have a trig function and an exponential function. There is this rule Liate, which I'm going to look at afterwards, which suggests to differentiate the trig function before that. So let's differentiate this and integrate the e to the x. The other way would also work, but let's just do that. And the first expression we have is just integrating this e to the x. So we have sinus x, we leave untouched, and we have e to the x here integrated, and then we write down the integral where we both differentiate and integrate. So we have cosine x e to the x dx. Now again we have an expression which we have to treat with integration by parts. So let's differentiate here and integrate this again. So we have sinus x e to the x. We integrate, just leave the cosine x the same, integrate, and now we integrate and differentiate. So if you differentiate that, we get minus. So we have to actually get minus minus. So this is plus and then we differentiate this. This is minus sinus x integral minus sinus x e to the x dx. So again, we see that we have a little bit difficulty with keeping track of all these minus signs. But what we have is what we have here is again the same expression we started with. So that's why it's called merry-go-round. Merry-go-round means we start with an expression here, and actually we end up with the expression again. So let me just write that down. Sinus x e to the x minus cosine x e to the x, and then minus, and then we just write this expression e again, I. So this is the thing. So we end up with the same thing. So that's a merry-go-round. And what we can do is actually just solve for I. So we get I is equal to sinus x e to the x minus cosine x e to the x over 2 plus. That was the merry-go-round. Okay, let's look again at this example. X squared times cosine x. We have suffered quite a bit here. I mean, not suffered, but it was kind of painful. We had to do it twice, and we had to keep track of all these negative signs. There is a method which I learned from a movie, Stand and Deliver, which I will show you just after that. Which is called the tabular integration method. It's absolutely cool. So what we do is we make a little table here. So what we start with is we start here with I'm writing here x squared, and I'm writing cosine x. This is the second function, and I add a third column here, which is a sine column. Now what we do on this side is we just differentiate. So here I differentiate everything, that's the first time I get 2x, then I get 2, and then I get 0. So we differentiate here. And in this column I'm integrating. So cosine x, when I'm integrating that, I get sinus x. I integrate again, I get minus cosine x. I integrate again, I get minus sinus x. Now in the third column we just put plus, minus, etc. So we take plus, minus, plus. And now comes the tic-tac-toe. So what we do is we just make tic-tac-toe and write down everything what we have here. So x squared times sinus x times plus 1. So that's the antiderivative is x squared times sinus x times plus 1. The second one is minus gives us plus, so 2x times cosine x. And the third expression here is a minus sign. This is plus, minus, so this is minus 2 sinus x. That's the tic-tac-toe method. Let's just do another example, just for fun. It's a lot of fun. Integral of x to the 5 e to the 2x. Make a table, 3 columns. First column we put x to the 5. Second column we put e to the 2x. And in the third column we put the signs. So we differentiate here. We get 5x to the 4th. We get 20x to the 3. We get 60x squared. We get 120x. We get 120. And finally 0. Just maybe make division here so that we don't mix that up. Now here we integrate. In this column we integrate, so we get e to the 2x over 2, e to the 2x over 4, e to the 2x over 8, e to the 2x over 16, e to the 2x over 32, and e to the 2x over 64. And we also have the plus minus And again, we are doing a tic-tac-toe. So what we do is we go like this, add up everything like that. So what we have is, just start here, x to the 5, e to the 2x half. Here with a negative sign, minus 5x to the 5x to the 4, e to the 2x fourth. Then comes the 20 plus 20x to the 3, e to the 2x over 8. And then comes the 60 with a negative sign, because we have a negative sign here, 60x squared e to the 2x over 16. And then the 120 with a positive sign again, 120 e to the 2x over 32. And finally we have just 120, actually that was already 120x. And then we had the 100, so that was the second last one. The last one is minus, with a negative sign here, 120 e to the 2x over 64. Plus c. That's the tic-tac-toe method.
Try the shortcut. This is easy. Baby stuff. We're Boy Scouts.
Kimo, my mind don't work this way.
Tic-tac-toe. It's a piece of cake upside down. Watch for the green light. Pancho, I think that guy's got a bigger problem than you. Tic-tac-toe. Simple.